do a couple physics problems here. But first, I'm going to introduce you to four of my friends. First we got red G2, black G2. Okay, these are staples. They're really awesome G2s. Then we get to the really special ones. This one I affectionately call baby blue. Enough said. This is my newest favorite G2 in the lineup. Probably can't see it in the low quality video, but this G2 is affectionately called Dark Knight. It's because it looks like a black pen at first glance, but it's not. It's not even navy, it's a dark mix between navy and black. How cool is that? Alright, now that we got that out of the way, let's take a look at a couple problems that have to do with work. Okay, forces and how we relate work to them. Okay, so a problem that we've done before, we've got a box or a crate and it's being pulled along, and there are four different forces on here. There's the force applied, there's mg, there's normal, and there's the force of friction. Okay, now as this moves 40 meters being dragged against friction here, what's happening is all four of those forces are acting during that time. And what we need to do is calculate the work done by each force over that distance, and okay, so work done by each force, and we need to get the net work, which is something we haven't really talked about in class, but it's super easy. Okay, alright, so let's start with gravity. Okay, we've got mg acting down right here, force of gravity. Okay, so we know that work, well, let's put a little g here, work done by gravity, is equal to F d cos theta. Okay, so the force of gravity is going to be 490 newtons. Okay, that's equal to 50 times 9.8. Okay, 490. Alright, then the distance traveled is 40, okay, but check this out. The angle between that distance traveled and mg is 90, okay? So look at that, cos 90. So if we pull out our calculators, cos 90 is 0, okay? So since these are perpendicular, we're going to get 0 joules for the work done by gravity. Okay. Alright, now let's talk about the normal force. The normal force, they're drawing starting here and up. Okay, we've been doing free body diagrams where we'll say, alright, mg, normal, force applied, they called it FP, force of friction. So that's another way to represent that. Alright, and notice normal has gone down. It is less than mg because the force applied's got this vertical component right here. Okay? Alright, now normal is up and the distance is this way horizontal, so again the work done by the normal force is equal to 0 joules because the force and the distance are at 90-degree angles. Okay, let's talk about friction. Friction is this force right here, and they are drawing it down at the bottom of the box because that is where that contact is happening, causing the friction. On an FBD, we would draw it like this. Okay, so the work done by friction is equal to the frictional force times the distance traveled times cosine theta. And again, theta is the angle between the force and the distance traveled. Okay, this time we are going to get some work done. So we got to use the fun equation. Alright, and oh, actually we don't. Look at this. Frictional force is just given to us as 50 newtons. So we don't have to do mu and normal and all that. Okay, so we're just going to plug in numbers here. Force of friction is 50. The distance traveled is 40 meters. And theta. Okay, so the theta between here and here, alright, or we could say the distance is right here along the ground. This angle is 180. Meaning that friction, sorry, that's supposed to be cosine 180. Oops. Cos 180. Okay, so this means that the frictional force is acting in the opposite direction as the travel. Alright? Okay, so if you plug in cos 180, you get a -1. So we're doing 50 times 40 times a -1. And that comes out to -2000. Friction did -2000 joules worth of work. Okay, now our force applied. We'll do that one in red. Force applied is upward at an angle this time. They're not pulling straight horizontal on this, they're pulling up at an angle. Okay, so work by the applied force is equal to FD cos theta. So that force is 100, distance is 40, and the theta between the travel and the force applied is 37 degrees, so cosine 37. And if we multiply all of those out, we are going to get a positive 3,200 joules. Okay, now notice this. Another thing we could have done, we could think of it like this. We could say, oh, let's just go here and find the horizontal component of the force applied. Okay, so if we say FP in the x direction, what we are doing is F cos theta, so we're doing 100 times cos 37, okay, and that would get us this horizontal component. Now if we look at this right here, that is what we have done in this equation, 100 times the cosine of 37. So we have found the horizontal force applied essentially by using the work equation. Exciting stuff. Okay, now work net. Let's go back to the Dark Knight G2. W net, so smooth, is equal to the sum of all of these together. So we've got 0 joules done by one of the forces, 0 joules done by normal, 3,200 done by the force applied, minus 2,000 done by the force of friction. So our net work comes out to be 1,200 joules. Okay, now preview to the future here. Okay, stuff we're going to get into, and this is very important. Net work is equal to delta KE. Okay, so I'm going to say that here so you absorb it better next time we talk about it in class. You can always take your net work and set it equal to the change in kinetic energy. So if you have a network, that means that the kinetic energy changed, which means the thing sped up. Okay? Or if the network came out negative, that would mean that the thing slowed down. Okay, so this crate sped up between here and here as it was dragged along. Alright, now one more important thing with that. Let's say friction was canceling out the horizontal force applied. That would mean that the net work would be 0 because we get a negative 3200 and a positive 3200. It doesn't mean the thing wouldn't go anywhere. It just means that F net was 0, meaning velocity was constant as we drag this. Okay? And we get 0 change in kinetic energy if the velocity is constant. Okay, so kinetic energy is equal to 1/2 mv squared, and that's the next thing we're going to do in class, is learn that. Okay, so since there was a positive net work, that means that my kinetic energy went up, and we'll get this positive amount of joules. Okay, what I want you to do is pause the video, work this on your own, and then check your work. Okay, let's see how we did. Answer here is positive 1470 for the joules. Okay, and you need to have proven where that comes from. If you need to correct it, that's okay. Alright, but show where that comes from right here. Okay, work it until you get the right answer. Work done by gravity is negative 1470. And you do not get any credit for just writing these down in class. You have to show me all of your work on how to get that. The net work is 0 joules. Okay? And so if this hiker is going at constant speed, notice that the kinetic energy is not changing because the velocity is not changing. Okay? It doesn't mean the thing didn't go anywhere. It just means that velocity didn't change. Okay, so again, prove these answers, and I'll give you some credit for doing these examples in class. Alright, thanks for watching.